So that's our claim. So which one's that going to be? The high. I like it. Which makes the null? Yeah, the opposite. So is this going to be a one or a two-tail test? One tail. So now we want to see. We've got evidence. You've actually collected evidence. And everybody's got their own evidence, but we got the one in the group that we want to put forward. Right? She had the best results, so we want to put her forward. So it's going to be a one-tail test. I'll tell you what, on this one, I'm not even going to give us an alpha. Second step is this good enough to do z-scores with? Yes, because NP, which was, actually, to be honest, n times p would be 20 times, well, let's just, screw this stuff. I should have done it more times, but it's too bad. Let's just say normal enough, just to get this going. This step, I'm not going to give us alpha. So there's really no rejection region I can draw. I know it's going to be one tail. I know it's going to be up here, but all of our results are going to be based on our p-value. We're not given an alpha. I didn't give it to you. Too bad. When the book doesn't give you alpha, I don't know if you guys have read this yet. If the book doesn't tell you what alpha is, you assume it's 0.05 because that's the most used one. Here I'm just not going to give us an alpha to mimic real life. Fourth step is get my Z star. So she got a 35% success rate, which doesn't sound like great, but actually compared to 0.2, it sounds pretty good. What's going to go in here? Yeah, PQ over N. What P was 0.2. So Q, of course, is 0.8. N was 20.
Are we doing the math on her individual test or on the group of our tests?
We're doing it just for her results, period. Just on that 7.
How does N 20?
So how many times did she guess? 20 times. I like it. Is everybody cool with that? So N is always the total number of trials. And that sounds weird when you have people you're talking about. But each person would be a different trial that might have a different outcome. Right? Here, each person did 20 trials, did 20 guesses. I like it. So I don't know, what do you guys get for that? Let's see. We got that yet? I was going to intrude it in my head, but I don't want to. Hello. Now I get this. Is that right there? You got 1.68? 1.68? Yes? Okay, I like it. Now, what do you think about that just on the surface of that? 1.68. This is why it's kind of like, I don't know how to feel about that exactly. I mean, that's decently far enough away, but what did unusual used to be? It used to be at least 2 steps away. So it's not that, but now we saw a problem just a second ago that 1.645 was good enough on that last problem we did. So what's the p-value in our Z star? What's the p-value here? What's this? What's the area in the tail of 1.68?
How many people did do this? 18?
18. So of course you can have the idea that if you have a large enough group of people, it would be more unusual for somebody to not get a high number. Sort of the same thing as it would be really unusual to not have at least 2 people that have the same birthday when you have a certain number of people in a room. Yes, sir?
Well, at a 90% confidence interval, that leaves 5% each tails. The critical value is 1.645, meaning out of 20 people, you should get about 1 who's that far away, get 18, so that's pretty close.
Yes. So when we did those confidence intervals and we had 2 that did not include the real mean, do you guys remember that? So here's the next point I was going to make after this. So Jacob's already got us there. Is that just like we've done in the past, when you have enough people doing something, the probability that something unusual doesn't happen is low, which is really weird. Any given day, something weird is almost definitely going to happen because the probability that no weird things happen is going to be really, really low. Why is that? Because what's weird? A lot of things. So all it takes is one of those to happen. You go, a weird thing happened today. And you're like, well, yeah, of course, a weird thing happens every day. Do we have this p-value yet? Anybody get that yet? I think so. I looked it up a while back. Yeah, 0.465. Now that's kind of cool. If I use a standard 5% benchmark, so if it's less than 5%, so remember, alpha is the probability that something happened randomly. So if we say a 5% chance, if I got less than that for it to happen randomly, I'm going to say that's evidence that it didn't happen randomly, that there's a real thing going on. So from this one test, I would say that looks like, that's evidence that you're psychic. Now, please, I know in Stats 1, it's mostly all about getting some problem done, knowing the steps, plugging stuff in the formula. I totally get that. Jacob's point is a good one. The minute you get enough people doing something, it's much more likely that at least one of them will find something unusual, independent of if it's real, right? So I would have been really, really, really surprised if nobody got like 5 or more. That would have really freaked me out. But when you first see this, everybody got freaked out when you guys saw 7. I was like, okay, good, I'm not freaked out now when I saw that 7. Came in at the end, but I don't know if you guys are with me at all. Something unusual will happen. Now, let's do this again, all right? I'm going to test you now. Okay. Because I don't know if I can trust Nick. I don't know.
It's for science.
I don't know. So,
I did a card extra for you.
aw, thank you. So look away from you. Are you gonna cover your eyes?
Yeah.
Okay. All right, let me shuffle these up a little bit. The rest of you guys. Oh, this is so exciting. So watch. All right, you ready? Okay, go. Okay, go.
Square,
Okay, go.
circle,
Okay, go.
circle,
Okay, go.
bacon,
Go.
bacon,
Go.
star,
Go.
plus,
Go.
square,
Go.
circle,
Go.
star,
Go.
bacon,
Go.
plus,
Go.
plus,
Go.
circle,
Go.
square,
Go.
circle,
Go.
plus,
Go.
star,
Go.
bacon.
That's 6 there. I like that shit. What about, let's see, what about 6? Let's do 6 real quick. That freaks me out a little bit.
It's 1/3 less Z-score. It's that 0.3 minus.
Somebody kind of with me. I like to do this because, of course, you guys could talk to each other. Maybe you're going to meet somebody new. This is kind of interesting in the first place. Maybe somebody's going to Google this shit later. These are called Zener cards, if I remember correctly. Zener, named after the guy that created these cards. He didn't call it bacon, but you know. You guys all know what I'm talking about. Put hands to receive bacon from the hand dryer. Have you ever seen it? If this was 6 instead of 7, what would change in this calculation? 0.35, yeah, so 6 would have made this 0.3. Are you guys with me? Can I just do this real quick so I can see what this becomes? So if I do this instead, what z-score do I get? I get 1.12, which right there, if I just stop there, can you guys tell me, would that be impressive or no?
Oh, decent.
No, it isn't. Right, I'm not. I'm not like, oh, good. I don't know. 6 was still pretty good, right? It was definitely above average, right? I'd want to do this again, and if you get 9 or something, I'm not going to do it again because I don't want to put everything through that here. But that is kind of nifty. So there's several things. Yes, yes. How do you mean above 2? Okay. Above 2 standard deviations? Yeah. Okay, so that's one nifty thing to come out of this. What is unusual or not ends up being based off of your own subjective beliefs. So 2 is just something to get us going with this idea, because everything comes out to be around 2. 2 relates the closest to 5%, which is the basic one that most people use. But the big reason why you're not given an alpha in real life is because it's completely up to you what enough evidence is or not for something. That's why when you look up journal articles or you look up some some study, and you look at the actual study, the real scientific abstract of the study, and you see p-values everywhere. You don't see alpha worth shit. They're only going to report p-values because then they're letting other people decide if it's good enough or not. They could say in their paper p less than 0.05 for us was significant, but then they just report p-values because then everybody else can make up their own mind. And then they can do it again and see if they can replicate what the other people found. And that's why just one instance of something is nowhere near good enough scientifically to say that it's true. You have to try to replicate it in different conditions, with different people, so forth. Maybe. That's really kind of nifty, though. I'm a little... That is kind of neat. Last time this happened, I had somebody get 8 right, which is really impressive. I tested him, and he ended up getting 3 right the next time, so it kind of averaged out. You guys kind of with me? That did not happen this time, so that's kind of neat. All right, maybe. The other kind of cool thing, this has come up several times this semester, and I've said it already earlier, but just like the birthday thing, it inherently feels like it should be unusual for something to happen. For 2 people to have the same birthday, for one person to get 7 or more right, it feels like that should be really unusual. But because it could have been anybody in this room. It's not just the probability of one person, it's the probability of anybody. It's much higher chance than we think that that's just going to happen randomly. Okay. Oh, let's see. Any other questions on this? I really like the average came out to be really close to 4. It didn't have to. But it should have been pretty close to 4 if nobody in here had, if not too many people had ESP. Just one person does. That's right.
How many people do you need to test to make it more likely than not that someone gets all 20 right?
That would be a really cool probability problem. What's the probability that somebody... All right, let's do this. A little review. What is the probability that somebody would get all 20 correct?
0.2 to the 20.
Yeah, 0.2 to the 20. Yeah.
I mean, how advanced do you want to go? Because obviously you know you can only throw in somebody of each symbol.
So what we would do is we would shuffle our stuff back in. The only reason I wanted you guys to go through the pack was to make sure that you end up with 20. Nobody went like over or under. Right? But you got another good point. There were only so many symbols in the pack, so the probabilities were sort of dependent. But the fact that you were guessing and you hopefully weren't giving them an indication if they were right or not, because then they could start to count cards if they wanted to, right? And that's the kind of thing you open yourself up to if you only have a finite set. So normally what you do is you either have a set, and when you guess, you shuffle it back in. You guess, you shuffle it back in, so all the probabilities stay the same. I just wanted to try to keep this as easy as I could, right? I like it. Okay, so anything else about that? Hopefully that was kind of cool. I never know what's going to happen. It was entirely possible that nobody got more than 4. That was a complete possibility. But I'm a probability guy. I'm like, that's probably not going to happen. And it did. Yay. Okay. All right. Should maybe test yourself later. Okay. So there are a couple, if there's no more questions over that, there are a couple things I haven't talked about yet in chapter 9. If you've been doing the homework, you've run up against them. Like the types of error. I think it's in the second section. So let's say we do have a court case. Let me ask you this. In general, yeah, you guys can go back. In general, for a hypothesis test, how many outcomes can I have? How many different outcomes can I have?
Guilty, not guilty, or liable, not liable. It's like a civil or criminal.
Yeah, either we can reject the null, or we can fail to reject the null. I like it. Yeah. That's the two things we can do. Now, reject and null is the same thing as support the high. So I'm not going to write that up here. If I say the one guy's wrong, that means it looks like the other guy is right. So these are the only two options. They relate to Z star makes it in the rejection region. Z star doesn't make it in the rejection region. It's the only two things that can happen. When would me doing this be a mistake? And not like you made a mistake in your calculations. You do all the work right. We know the statistics has a probability that we're wrong. So when would me saying this be a mistake? If I reject the null, when am I wrong?
Is that what you're claiming?
Claim doesn't matter where shit. Sorry. Claim doesn't matter. If I reject the null, when is that wrong? If I say the null is wrong, when am I incorrect for saying that? If the null is actually right. There you go. So what we call a type 1 error is when I reject a true null. That's a type 1 error. And then the type 2 error is going to be the opposite. And when would this be a mistake? If I fail to reject, if I fail to show he's wrong, I'm incorrect if that really is wrong. So type 2 error is fail to reject a false. If I fail to reject it and it's actually false, that is an error. Is that a mistake I made in the work? No. That's an error inherent in the fact that we can never be certain. Same thing as you either can kill somebody who's innocent or you can let somebody guilty go free. You guys kind of with me? So that whole idea. We're not going to get into the philosophies involved. So let's come up with a real life thing. Not even just the courtroom, because you can talk about the courtroom to death. But I like to do something like this. Let's start with the courtroom a little bit, just to get us going. In a court case, what is your assumption in the United States? Yeah, your null is that the defendant is innocent. And the burden of proof is on the person making the claim that that person did something bad. So I'm assuming, don't get into all the different types of law and bullshit. Let's say this is criminal court about somebody who killed somebody. Let's just make it completely straightforward. It's not small claims court or some shit. Don't bring that in. Is this civil? No. So what is my alternate? This is remarkable. What's the alternate going to be? Yeah, the defendant is not innocent. I like it. Let's just put guilty. So what would a type 1 error mean? So if you've done the homework, you've seen this problem in the homework. What would a type 1 error mean? Well, what would it mean is real? What's true? What's the truth? If you've made a type 1 error, what's the truth? The defendant's innocent. That's the truth. But we think he's or she's guilty. I like it. So type 1 in this case would be defendant is actually innocent. But we think they are guilty. And obviously, what would a type 2 error be? It's kind of nice to see a problem that's less mathy. Type 2 error would be the defendant is actually guilty, but we think they are not guilty. Okay. So if you've done some of the homework, I think it's in section 9.2 where it shows up the types of error. Now, I'm not going to get too deep into some of the other aspects of hypothesis test, but let me just give a little teaser to those of you that might be interested. The type 1 error, you can control this directly. The type 1 error. If the null is true, when would I say it's not true? We think that they're guilty. So type 1 error is, I think the null is wrong. So that would only happen if we actually made it out here, right? If this really, now I know this isn't mathy, and I know this picture doesn't really work. It's like, is innocence and guilt normally distributed? All right, just let go of that for a second. If this is innocent here, and I get out here, if they really are innocent, what's the probability that I would find evidence out here that's equal to alpha? Alpha is the area of the tail, which is the probability that something happens in there. So alpha is the probability of a type 1 error. Alpha is the probability of a type 1 error. So if a type 1 error in your situation is bad, you're going to make alpha smaller. Your own personal alpha would be smaller. Does that make sense? Now, unfortunately, the type 2 isn't that easy. Type 2 is actually the symbol called beta, is the probability of a type 2, and it's not equal to 1 minus alpha or something. It isn't. There's an interesting relationship between the two of them that I'm not going to get into. This is related to something called the power of a hypothesis test. These are the things that you can look up if you want to. Beta is like alpha, alpha, beta, but it's the probability of a type 2 error. The math involved in calculating it involves alpha, but not directly. And it's related to what's called the power of a hypothesis test. So if you Google that, if you want to see some more, if you take stats 2, you'll definitely get a lot deeper into this. Because you would go with hypothesis test, but then you get a little deeper in what's the power of this test. Okay, maybe. Obviously, this much should make sure. The smaller I make this, the bigger I make this. And vice versa. Right? So it depends on which error is worse to make. Now, that's very often subjective. Which error would be worse to make here? In this case, if it's a murder case, what's more than likely going to happen to the person eventually, maybe? The defendant, they're actually innocent, but we think they're guilty. So they are probably going to be put to death for something they didn't do. Right? One-armed man, all that kind of stuff. Bus flips over. This case, what happens? They did kill the guy or girl or whatever, but we let them walk free. So do you see how it's very subjective about which error is worse? Okay, that's why they let each jury determine their own level of evidence. I'm not going to make this into a political or like a criminal law course or something. I'm not qualified to talk about that. Yes?
For the second one, what you just said, can she also say that it could happen again?
That goes into the subjective feel for what's worse. If you let this person go, will they kill again? But then it's kind of like, do you bring that in when you're like, I'm not sure if this person did this. I'm not sure if I'm going to put them to death. But if we let them go, they might kill again if they killed, but I'm not sure they did. Oh, shit. Do you see how that's like all wrapped up? Okay. So I'm not saying it's clear cut. That's why I love statistics. It's able to get closer to this kind of thing because it's very messy. You could always make a mistake. That's why I never want to be in a jury that puts somebody to death. I'm sorry if you ever were, ever will be. I was on a jury, but it was just over money. So I was like, all right, whatever. Everybody involved had a ton of it, so who gives a shit? But anyway, so nobody had to be put to death or anything, thank God. Okay. Maybe. So it's the type 1, type 2 error that came up in the homework. I'm trying to remember, there was something else I wanted to talk about. If I can't remember the 9 stuff, I want to get into 10 a little bit, and then we'll call it a day.
According to Todd, the percentage of erroneous death row convictions is 4%.
That they know of.
They consider this.
Yes. Yeah, you never know. Okay. So I'll remember sometime. Oh. By the way, let's do this. Let me make this official. Our next test is May 8th, if I remember correctly. Next class is May 1st. I want to have a quiz. Oh, shit. Really, Jeff? Yeah. I want to have a quiz on Chapter 9. So next class we'll start with that quiz. I'll have the practice test, right? Okay. So I want to get a little bit, I want to do chapter 10 a little bit. You gotta go. And then we'll call it a day. What I love about this, I think it was
What one is we going to put on the quiz?
all the ones from chapter 9. So Z star for P hat, Z star for X bar. That's the really ones you need. Yep. Cool. Okay. The thing I love about, I think it was, is it 10-2 I assigned? I can't remember. Do you have your homework sheet? Yeah, 10-2. Okay, good. I wanted to do the most straightforward section out of here, just to give you a taste for what happens. If you notice something about all of mathematics, including physics, you start off with situations that are idealized. For example, we started this whole thing off with z-scores, knowing the mean of the population, knowing the standard deviation of the population, and that very often does not happen. And then we got hypothesis tests, but we still had kind of a known mean or something to compare it to. So if I'm testing some brand new drug, it's never been tested before, I don't have a clue what to expect. I have nothing to compare it to, really. So what I normally do is I compare two samples, right? I compare results from one sample that took the drug, and I compare it to another one that didn't. And of course, if you get further in statistics, you're able to do multi-group comparisons, ANOVAs between like the control group that gets nothing, the placebo group, and the medicated group, right? Not they didn't come medicated, but they become medicated. What we do in 10.2 then is we have two samples that we take. So recall, this is true here. And let me kind of rewrite this again. Let me put in here the formula for this guy. That was that new standard deviation, right? So this one would be, so that is the, get out of there, Jeff. You wrote the whole thing again. There you go, buddy. That's the formula that we use on that fourth step for hypothesis test about a mean, to see how far away our sample got. So we have this somehow, and of course we somehow have this too, which we're still going to have, but oh well, we're getting closer and closer to the reality. So what I want to do here is I want to replace this and this with two things. So for example, if I took a sample of men and a sample of women, and they got their average grades, I wanted to see, well, how different are they? Is there evidence that the men were bigger than the women's grades, or the vice versa? Are you guys with me? Or they're not equal to each other? Okay. So I need to have two of these. I need to have an X bar 1 and an X bar 2. I need to have a sigma 1 and a sigma 2 for two different populations. So if I take a sample of men, they came from the population of men. Sample of women came from the population of women. I like it. I like it. So this is what I love about this. Now watch. Let me do a little bit with this guy. Let me just do this and see if you guys agree with me. Let me make one big ass. If I make one big ass square root, what's got to go on top so this is still true? What's the square root of what is sigma? Sigma squared. Okay, let me stop for a second. That's kind of silly. Is that true? Well, shit, yeah, Jeff. Square root of sigma, square root of sigma. That's, ooh, way to go, buddy. But now watch how this works. My claim earlier this semester was this formula basically never changes. Even with the p-hat shit, it was always our data minus the supposed middle divided by the spread, always. So watch what happens. It's kind of cool. What happens to this formula, we'll put it above this guy. Keep this guy, so that's the old one. What happens now is I've got X bar 1 minus X bar 2, so I got two of these. I've got two of these. All right, so I took this and I doubled it because I have two samples. I took this and I doubled it because I have two populations. And on the bottom, I'm going to take sigma squared over n. I'm going to make it sigma squared 1 over n1 plus sigma squared 2 over n2. I double it for two populations. That is a massive formula, right? It's kind of a big-ass formula. But do you understand how these are the same? Now watch. The ones I think I assigned to you were ones like this. If my claim that if I make a new drug, what claim am I fighting against? The mean for the old drug and the mean for the new drug. If I make a new drug, I'm fighting against the means being what? What do I think isn't true? Yeah, I'm fighting against the means are the same. It's like, ooh, you made a new drug and it does the same thing. Way to go, buddy. You guys kind of with me a little bit? If it was mean time, I try to show that the time was less. If it was whatever. Mean weight gained. If you're on some medication, I want to show that my weight gain is less than the other one. Something. You guys kind of with me? Okay. Which means if I'm fighting against this, if mu1 is mu2, then what's this? 0. So that is almost always what it is. It doesn't have to be. But most of these claims between two samples will have this, which means this piece goes away. So what you end up with is this, and I love this formula. You just end up with this without those, but I know. But let me just write it again. I'm
crazy.
This is how relatively far apart the samples are. Right? This is the difference between the sample means. That's how far apart they are, divided by the spread. So this is how relatively far apart the samples are. So if I have a new drug and I'm trying to show that it's less time than the old drug, then they've got to be so far apart. Those two samples, their times have to be so far different. That's why I have this difference up there. How different are the two samples? I love that idea. What would change in this formula if I didn't know sigma? Two kind of things would change. What would I put here if I didn't know sigma? S. If I take a sample, I can figure out what the hell S is. And this would be like officially a T star, right? All right. That might be enough for today. So we'll do an example at 10-2 next time after the quiz. I'll have the practice test next time for the test. Okay. I think that's enough for today. Go home and work on your ESP skills. Or maybe don't. I don't want you in my head.